So today we will start chapter 6. So finally, 2 more chapters remaining. So one of them is the chapter 6, which is thermodynamic models of real pure compounds. And here in this chapter, we have 4 points that we need to cover. So hopefully today we can finish the first 2 points. So we will start with a quick revision of basic laws that you know these laws from calculus courses. And then we will explain the fundamental property relations. We start talking about the fundamental property relations and Gibbs relations in chapter 4. So we will continue this discussion in this chapter. Once we finish these 2 points, then we will start talking about the mathematical models of thermodynamic properties. How we can develop a model in order to estimate or calculate the thermodynamic property for different pure compounds. And then we will have another way to calculate the value of these properties by using what is called residual properties. As we said in previous lecture, this chapter has a lot of math derivations in this one. So this is why it's important to know what the mathematical concepts we are talking about. So in this chapter, as we have these 4 points, so for the basic law of calculus, we have 3 rules that you should remember. The first one is the total derivative. We have the triple product rule. We have expansion rule. So we'll use all of these rules in the derivation. Also, we have the property relations. These relations can be fundamental relations, can be Maxwell relations, or either can be other relations that we have discussed before. So we will talk about fundamental relations. And the fundamental relations, we have 4 relations. 1 for internal energy, 1 for enthalpy, 1 for Gibbs free energy, 1 for Helmholtz energy. Then we have Maxwell relations. We will explain these relations, what is the type of these correlations. And then we have other relations, such as heat capacity, thermal expansion coefficient, isothermal compressibility coefficient. All the relations we have, from here to the top, the basic laws of calculus, property relations, all of these relations, so we will use in your derivation. Okay, we cannot make any derivation or derive any model for thermodynamic property without knowing all of these relations and how we can use them. Okay, so this is the whole idea of this chapter. So understand these calculus rules, these laws, these thermodynamic relations, and then play with them in order to derive our model. So one of the things we have, we should understand why we can need to develop these models. We already have some appendix. We already have figures. We have some basic relations we explained in previous chapters that we can use to find the value of the thermodynamic property. So one of these things similar to this example. So this is one of the examples that we solved before. We have ammonia vapor. This ammonia vapor goes to a throttling valve, which is adiabatic, steady state. The inlet at 30 degrees Celsius, 1 megapascal. The outlet is 1 megapascal. Then we have figure, we have appendix. We can use them in order to find the outlet temperature. So what we did in previous chapters, we have this substance. If it's steam, for example, then we have steam tables. We can use the steam tables, find any property that we need. If it's ammonia, similar to this example here, we have figures related to ammonia, similar to this one. All the thermodynamic property that you need for ammonia, you can get from this one. Because this is the relationship between enthalpy, y-axis is pressure. Here we have many lines. So one of them or some of them represent entropy values, others represent the temperature. So you can use appendix or you can use figure like this one to find whatever property that you need. And the whole rule in this one, or how we can using this one. So for example, here we have ammonia and we have valve. So we know that we have valve, throttling valve, and if you remember from the analysis of chapter 5 or even the last lecture, throttling valve, it means what is the property that is constant? Enthalpy. So we have throttling valve, so this one means we have constant enthalpy. So this means enthalpy of the inlet to this valve equal enthalpy of the outlet to this valve. And for the inlet, I have given information. So for the inlet, I know that the pressure of the inlet is 1 megapascal, which is equivalent to 10 bar. The temperature, it's 30 degrees Celsius. This is also given. So you can use this figure, and from this figure you can find the inlet enthalpy. And this one will be 1500 kilojoule per kilogram. And then, so for the outlet, I know that the enthalpy of the outlet is 1500 kilojoule per kilogram. Pressure of the outlet, so this one is 0.1 megapascal, which is 1 bar. So again, from figure, you can find the temperature of the outlet, and the temperature of the outlet will almost be like 3 degrees Celsius. And this is what we need to find. So basically we have this figure. So we have any value of pressure given, just put it on the y-axis. So we have, let's say, the enthalpy for the outlet. So we can see the intersection between these 2 points, and then we can figure out what is the temperature between this one. So this is the easy thing. We have figure, we have tables, use the figure, use the data available in the table, and then find any thermodynamic property you need. Okay, but the question is, what if we don't have available data? What if we don't have figure like this one? If we don't have any appendix, what we can use? We examine this for ideal gases, for internal energy and enthalpy calculation, because we explained heat capacity at constant pressure, heat capacity at constant volume, and we have an equation to calculate enthalpy change based on Cp value, entropy change based on Cp value. So this is what we did so far. But the question is, what we have like more thermodynamic properties we need other than the internal energy, other than the enthalpy from this one. So this is one, if we don't have like data existing to help us to directly use, then there is no solution except to derive a mathematical model. And when you hear this word mathematical model, then we are talking about mathematical equation. We have a mathematical equation that we should substitute in this equation, and from this substitution we can find the value of any thermodynamic property we need. We have in general two advantages for any thermodynamic or for any mathematical model. The first one, it helps you or enable you to solve any problem in case of if you don't have available figures, if you don't have any appendix or tables available, and it makes you more understand the process, give you like deeper understanding of what changes happening, what are the factors affecting any process. If you have internal energy, so what are the factors affecting internal energy for this process? Entropy, what can influence the value of the entropy for this process? In the mathematical derivation, we have like some foundation we should understand, which is some basic laws of calculus, and then we have some fundamental relations. And what you will do in this mathematical formulation is something similar to this one. This one also, only we are like playing with some math rules in order to try to find a mathematical formula that it's easy for us to substitute in this formula and find the value of the physical property. So this is everything that you are like planning to do during your like developing of this mathematical equation. So the thing is how you can play with these things. So all of the figures, all the changes, everything in this figure, just we have some basic laws of calculus, we have fundamental relations, and then your rule is to know which one of them you should use at this moment in order to like change or simplify your mathematical equation. And this is what we need to practice in this chapter.